In this section, we will be solving quadratic equations. The general form of a quadratic equation is ax squared plus bx plus c equals 0, where a, b, and c are generally thought of to be integers. Now, I'd like to break this into a few different cases. In the first case, we're going to let c equal 0, leaving just the ax squared plus bx equals 0. Let's choose some numbers for a and b. Let's go with 8x squared plus 11x equals 0. Whenever c is equal to 0, there is no constant term, and therefore an x can be factored out of the first two terms here. X, in this case, times 8x plus 11 is equal to 0. We then have x is equal to 0 or negative 11/8, and the solution set contains the values 0 and negative 11/8. In the second example, we're going to let b equal 0. Let's try the following equation. 3x squared plus 6 equals 0. Notice there's no bx in the center. I'm going to, in this case, isolate the x term on the left and then square root each side. We're going to have x squared is equal to negative 2, and therefore x will equal plus or minus I root 2. And those will be the values that are in the solution set. If a is equal to 0, then you really don't have a quadratic equation at all. Let's say we have 0x squared plus 4x minus 7 equals 0. We can just ignore the 0x squared. Solving this linear equation, we have 4x equals 7, and therefore x is equal to 7/4. Let's solve this quadratic equation in three different ways. The first and easiest method is to factor, if at all possible. Here we have x minus 5 times x plus 3 is equal to 0. And this implies that the solution set will contain 5 and negative 3. This is always the easiest method to try first. Now let's try looking at the quadratic formula. Now, instead of going straight to the quadratic formula, I like to evaluate the discriminant first, b squared minus 4ac. In this case, we will have negative 2 quantity squared minus 4 times 1 times negative 15. This gives us 4 plus 60, which is 64. And it turns out that the value of the discriminant will always be a positive perfect square whenever the original expression is factorable over the integers. Okay, let's now solve. X is equal to negative b plus or minus the square root of 64 all over 2a. X is equal to negative b, that's negative of negative 2, which is 2, plus or minus the square root of 64, which is 8, all over 2a. 2 times 1 is 2. Now we have two choices, addition and subtraction. If we add the 2 plus 8, we get 10 over 2, which is equal to 5. And if we subtract 2 minus 8, we get negative 6 over 2, which is negative 3. Notice we have the same solution set as before. Now let's solve the equation using the complete the square process. I'm going to rewrite the equation with a blank on the left-hand side and move the constant term to the other side. There is no leading coefficient to divide off of each side, so I'm going to begin the complete the square process by cutting the middle coefficient in half, writing that value on the next line, squaring this negative 1 to get positive 1. Now when I write 1 in that blank, I've added 1 to the left side of the equation, so I need to add 1 to the right side of the equation to keep the balance of the equation. I'm next going to complete the square on the next line by inserting the x, the parentheses, and the quantity squared. Notice that x minus 1, quantity squared, yields the line above, and I'm going to combine the terms on the right-hand side to get 16. Now, square rooting each side, we have x minus 1 is equal to plus and minus 4. Therefore, x is equal to 1 plus or minus 4. If we add 1 plus 4, we get 5, and if we subtract 1 minus 4, we get negative 3. So here we see in a third way the solution set is 5, negative 3.